So I'm going to go ahead and get started. Welcome, everyone. Okay. Yes, you can do that. Just like email it to me or text me or whatever. Yeah, I'll try. I can get back to you tonight at some point. Okay. Anyway. Okay, so I'm only going to go over what we did last Wednesday and Friday, since we didn't have class Monday. And I'm going to leave the stuff we learned today and for next week to let that stew a little bit. Okay, so last Wednesday, we went over cycloalkanes, right? So here's their general formula is CnH2n. And you remember regular straight chain alkanes, or alkanes in general, their general formula is CnH2n plus 2. But cycloalkanes have 2 less hydrogens because we just took off the 2 hydrogens at the end and put the chain together to make a ring. So cycloalkanes are organic molecules where all the CC bonds are single bonds and they form a ring. The bond angles can affect its stability because of the ring structure. So remember, so with like cyclopropane, this is just a triangle, right? So this angle right here is only 60 degrees. But for tetrahedral carbons, for sp3 hybridized carbons, we want a bond angle of 109.5. So that puts a lot of strain on this bond, and the bond's too tight. So it's not very stable. And same thing with cyclobutane, because this angle right here is 90 degrees, and again, we want it at 109.5. So again, it's too tight, and it puts a lot of strain on the molecule, and it's therefore not stable. So you really don't see too many of these at all. Your cyclopentane and cyclohexanes you're going to see the most of. For cyclopentane, this angle is just a pentagon, is 108, which is pretty close to 109.5, so this is pretty stable as is. For cyclohexane, though, this internal angle right here is 120, which is much too big. So cyclohexane goes through something called puckering. I like to think of it more as like crumpling. I have it made right here. I'll try to show people online too. So this is just like regular one plane cyclohexane, but it doesn't really look like this in real 3D space because just this area here is just too big. So again, I like to think of it as crumpling. So you can either have chair or boat conformation, and you're going to do this in lab, by the way. So boat conformation, I hope you can see that. So these 4 carbons here are coplanar, and then these 2 on the ends just go up, and it's like a boat, okay? Or you can have chair conformation where one of the end carbons is up and one of them is down, but these 4 in the center are still coplanar. Does that make sense? So you'll build those in the lab, but I just think it's a bit easier to see. So, and that tightens those bond angles so it can be more stable. And those are called conformations, right? It's chair and boat, and about, I think it's like 99% of cyclohexane is in chair conformation because it's much more stable. Okay. So naming cycloalkanes, we did that too. Pretty simple. It's nothing too different from what you did with just regular alkanes. Let's see. So you just assign side groups the lowest possible numbers, just like regular alkanes. You're still using the suffix ane because all of these bonds are single bonds. You're using the same prefixes for however many number of carbons are in the ring, so like propane, butane, all that stuff. And then you just put cyclo in front of it to indicate that it's a ring. So I want to try over here. Who can tell me what my parent compound is? How many carbons are in that ring? 6. correct. 1, 2, 3, 4, 5, 6. Right. So that's going to be cyclohexane, right? It'd be cyclohexane, but yes, hexane because there's 6 carbons and they're all single bonds. So my parent compound is cyclohexane. Okay, but I have these side groups. Okay. I need to assign them positions and names. So this is a chloro group, right? And these are just methyl groups. Okay. So I need to start counting my ring to assign positions. Okay, so I can either start counting at the chloro group or the methyl groups. And this one is a bit tricky because if I start counting here, I have 1, 2, 3, 4. Okay. If I start counting from the methyl groups, I also have 1, 2, 3, 4. So which direction do I count? Because both of them have numbers 1 and 4 on the side groups. So if you ever run into this, no, but close. So if you ever run into this, you assign the lowest number to the group that's going to come first in the name. Okay. So I have chloro, starts with C, methyl starts with an M. I want my chloro group to have the lowest number because that's going to come first in the name alphabetically. Okay, so I just count the first way. Oh, shoot, why did I just do that? My bad. Anyway. So yeah, I'd count this way because that gives my first group that's going to be in the name the lowest number. Okay. So my IUPAC name, yes. So it'd be 1 chloro dash, I have to put 4,4 dimethyl cyclohexane. Everybody got that? Does that make sense? Okay. And if you just had like one group on the ring, like this, then it'd just be chlorocyclohexane. Because you don't have to put a number if there's just one group, because all of these carbons are identical. So you just would assume that it doesn't matter which one is number 1. Yes, because there's 2 methyl groups there. So it's going to be dimethyl, but then I have to indicate where they're at, and they're both on carbon 4. To be 4,4 dimethyl. Okay. Are we good on this one? Gotcha. Okay, so the next thing we went over is cis-trans isomerism. So this happens when you have 2 identical side groups on a ring. They can either be on the same side of the ring or different sides. So they can both either be on top of the ring. So if this is my ring, I can have both of them on top, or one on top and one on the bottom. So cis means the same side, trans means different sides. And these are called geometric isomers, which are isomers that have the same molecular formula, the same connectivity, but different geometries. So as you see, these both have the same molecular formula and the same connectivity. This methyl group and this methyl group are both connected to the same carbons on both sides. But the difference is, for this one, I have both my methyl groups in front of the plane, so coming forward. And on this one, I have one in the front and one in the back. And this is a cis isomer, right? For cis isomers, it doesn't matter if they're both in front or both in the back, because you could just flip the molecule over and it'd be the other one. So as long as they're on the same sides, it's still cis. Okay, so for naming for cis-trans isomers, it's just the same thing as naming cycloalkanes, but you have to indicate cis or trans before. So this one would be cis 1,2 dimethyl cyclohexane. And this one would be trans 1,2 dimethyl. Does that make sense? Does everybody get where I got those names?
So that one was trans because it's got the methyl in the back.
Mm-hmm.
Okay.
Yeah. I'll actually build this with my handy dandy molecule set. Okay, so I don't have all the hydrogens on here, but just pretend that I do. Okay, so this would be trans 1,2 dimethyl cyclohexane, because this is my plane, and I have one methyl group in the front and one in the back. And then if it was like this, then it'd be cis, because they're both on the same side. Does that make sense? Okay. So what we did Friday are halogenation reactions. This is where it gets a little bit tricky, but nothing we can't handle. So for these reactions, you need your alkane in excess. So that ensures that you're just going to have mono substitution. If you have your halogen in excess, then it's going to start substituting on more than one hydrogen and give you a bunch of products that you don't want. Okay, so we want to have our alkane in excess. To facilitate the reaction, you need to shine a light, which is what this symbol means. It means there's light being shown, or heat it up. You're going to see this probably most often because it's just easier to write than heating up. And this is a 3-step reaction, as you can see in this mechanism. So we can go ahead and go over this. So this is cyclopentane, right? And halogenation reactions can happen with cycloalkanes or any other kind of alkanes. So this is going to be in excess. Then I'm going to add my bromine, shine a light, and then my product is going to be just bromocyclopentane, and then HBr. So the mechanism for this, our first step is initiation, which is where we take our first bromine molecule and you break it up into 2. So our reaction arrows, remember, if you're showing the transfer of 2 electrons, then you're going to use a full arrow. But because we're only showing transfers of 1 electron, you're going to show half arrows. Okay, so all those red arrows are half arrows if you can't see them. So in this bond, in between bromines, there's 2 electrons there for that bond. So when this bond breaks, 1 electron gets transferred to one of the bromines and the other one gets transferred to the other one. So that makes 2 bromine radicals, which you can see the radical because I have 1 unpaired electron on those. And these are very reactive. So now we can start propagation, which is these 2 steps of our reaction. So my bromine radical is going to attack one of these hydrogens. Remember, on all of these carbons, there's 2 hydrogens. It doesn't matter which one it attacks because they're all identical. So, and I just drew one just to emphasize that. So this bromine radical is going to attack this hydrogen. So you can see the half arrow because this 1 electron is being transferred to this hydrogen. This bond between carbon and hydrogen is being broken. Okay, that's a bond of 2 electrons. So one of my electrons is going to go to this bromine hydrogen bond, and the other electron is going to stay on my carbon and make a carbon radical. Okay, so from this, I make my first product, HBr, and then I make my alkyl radical. You following me so far? No? Do the arrows make sense, or are arrows what's messing you up?
This is the class we missed, and so I'm just studying.
Okay.
We haven't watched something yet because he didn't turn his mic on.
Right.
So.
I'm pretty sure the mic was on because I paid attention to that. I don't know what happened with that. Sometimes just the recording gets messed up, but I'll do another one after this. It'll make a bit more sense. Okay. So after I make my alkyl radical, then again, radicals are very reactive. So it's going to attack my next molecule of bromine. Okay, so I have 1 electron here. It's going to attack this bromine, hence the half arrow. I have a bond right here that is 2 electrons in it. So one of these electrons is going to get transferred to my second bromine right here to regenerate a bromine radical. And the other one is going to go to this carbon to make a carbon-bromine bond, which this right here is our second product. And for the steps, okay, so our initiation step, which is this one right here, this only needs to happen once, right? Because we just have to break that first molecule of bromine to make our radicals, and then these second and third steps can happen over and over and over again in a cycle until we run out of reactant. Does that make sense? So, like I said, for this third reaction, we regenerate this radical. So then I can go back to this reaction and do it again. So this only needs to happen once. It doesn't just happen once. It happens to a very small percentage of the bromine, but you only really need it to happen once to start this whole cycle. And it doesn't stop until you either stop shining the light, stop heating, or you run out of reactant. Okay? So, do you want me to do another one of those? Okay. I have a slide for it. Let's see. I'll do ethane. Okay. Anyone want to take a stab at what my products might be?
Is this like what it would look like on the test? Like we'd have to find the products of it? Is that the
So he'd probably like ask you something like this and ask you for the product and then ask you for the mechanism.
So like for the initiation step, you'd have to like separate the CH3s. So
You'd separate, okay. So for initiation, you're separating your halogen, right? You're not separating your alkane. Yes, thank you, Carol. So yeah, I'll go ahead and write our products and then we can go from there. So these would be our products, right? Because we just put one of the chlorines on ethane and then the other one gets merged with that other hydrogen. Okay, now we can do the mechanism. So for initiation, you're breaking apart that chlorine to chlorine bond. Okay, so chlorine is a diatomic molecule.
So it's always going to be that like extra one. Like the one. It's just
Hmm?
Okay.
Okay. All right. So chlorine. You don't have to show this, but it's a bit easier. So chlorine has 7 electrons, right? But these are bonded together, so they both have 8 right now. So in initiation, I want to break these 2 chlorines apart so I can make radicals. So in this bond, I have 2 electrons in it, but I want to make a radical. So with a half arrow, I'm going to show 1 electron is going to this chlorine, and the other one is going to that other chlorine. And then I'll make 2 chlorine radicals, which you show a radical with just a dot. Okay. Does that make sense? Okay. So then my alkane comes in, and this is just our first step, right? Initiation. And then I start a second step, which is where I introduce alkane. And I'm going to draw it like this because it's pretty important to show that bond so you can see what's going on. But that's still just that. Plus 1 of my radicals. Okay, so radicals are very reactive, right, because they have an unpaired electron. Let me get my red. So this electron is going to come over here and transfer to this hydrogen, okay? And this bond right here has 2 electrons in it. So 1 of my electrons is going to go to this carbon and make a radical, and the other one is going to go to my chlorine and make a hydrogen-chlorine bond. Bye. Thanks for coming. Okay. So from that, I make an alkyl radical, right? Because I broke that carbon-hydrogen bond and HCl, which is my first product. Okay. So now we can go into our third step. So for my third step, I have this ethyl radical, which is very reactive, and it's going to attack another molecule of my Cl2. So it's going to attack this. Oh, let me get my red. Okay, so I'll stay with red. So remember our Cl2 up here. So this step where it breaks it into 2 radicals, that only has to happen once, but it happens to a very, very small percentage. Okay, because our light or whatever is not strong enough to break every single molecule of Cl2 apart. So only a small percentage of our Cl2 gets broken into 2 radicals.
So it's basically consolidated.
Yeah. So most of our Cl2 is still connected to Cl2. Okay. So this radical, this electron, gets transferred to this chlorine. And then this bond here has 2 electrons in it. 1 is going to go back to 1 of my chlorines. And the other one is going to come to my carbon and make a carbon-chlorine bond. So I end up with CH3, CH2, Cl, and I remake my chlorine radical. So then these steps 2 and 3 just keep happening in a cycle. Does that make sense?
What's your product for the third one?
Oh, yeah. So, well, these are products for those specific reactions. But for the overall reaction, my HCl is my first product, and then my CH3, CH2Cl, which is this chloroethane.
The first part of the second one, or the first part of the third one, and then the second part.
Or is it just the one without that?
Wait, what? Sorry.
Your product for the third.
Okay, so the one at the top, that's my overall reaction. And then steps 1 through 3, that's my mechanism for the reaction. So I make my products in steps 2 and 3.
Yeah, but for the overall, like, to which ones, like the ones that you circled, why did you circle those specific ones?
Okay, because those are the products for my overall reaction.
Okay, so you always use the first part of step 3 in your products, and then you always use the second part of the second one.
I mean, it doesn't have to be rearranged in that specific way, but you're always going to make one product for your overall reaction in step 2 and then the other one in step 3.
Yeah, but why didn't you use the first part of step 2 and the second part of step 3?
You mean like,
You
okay,
can choose which one.
Yeah,
you mean like why didn't these, okay.
Yeah.
So the other product I made here is a radical, which I needed to have this third reaction, because this product is a reactant in my third reaction, in my third step, okay? And then this product, my chlorine radical, is a reactant in the second step.
so the products are just the ones without the radicals.
Yeah.
Okay.
Yeah. Your radicals aren't products. They're not stable. Like you can't isolate a radical. Okay. So those are just, those are my reactants for the other steps. And yes, this will probably be on the test, Carol. I don't know exactly how he'll test you on this, but yeah, it will most likely be on the test. Anyone else have any questions? Yes.
How do you know which ones will be radicals? Is it always the one that gets the electron?
So let me think about how to answer this. For like which step? 2 and 3. Okay. So I know this forms a radical because I'm taking away this hydrogen. Okay. So I'm breaking this bond and I'm not replacing it with anything else but one of these electrons. So I'm making it radical. I feel like that doesn't make sense.
Step 3 is because you're taking away one of the COs.
Mm-hmm.
Okay. I see.
Yeah.
I didn't know which one to give the half arrow to. Like for the CLs, you have to break the bond, but how do you know where to transfer?
Okay. So for like the first step, right, I have 2 electrons in this bond right here, and I break it, and 1 goes to each chlorine. And the second step, this 1 electron is going to attack my hydrogen. Huh?
I can't see what
Oh, yeah, my bad. No, you're okay. Okay. So in my second reaction, this unpaired electron is going to attack my hydrogen. Okay. And this bond with 2 electrons gets broken, and one of the electrons goes to carbon, which makes this radical. This unpaired electron is on carbon. And then my other electron from this bond goes to this hydrogen chlorine bond.
Yeah, but how do you know which direction to compare them? Like how do you know where to?
Okay. So for radicals are always attacking something, so your arrows are going to come from your radicals. Okay. So that's where those arrows come from, is because this unpaired electron is attacking something. And for these arrows, you're just splitting that bond into the 2 species. Don't get too caught up in the arrows. I don't think he requires you show the arrows,
Well, I
but
just want to know how you would get the product. And I wouldn't know if you just for your example, before you did all that, I wouldn't know what the product was if you didn't show there.
okay. So that will probably make more sense when you watch the recording of the class. Do you have that recording now?
Yeah, he emailed us.
Okay. Yeah, that will probably make more sense when you watch that. If it still doesn't, then email me or schedule a tutoring appointment with me. Yeah, I'm not sure how.
I'm sorry.
No, you're okay. I don't know how to explain it without I think it'll make more sense once you watch the class.
Okay. I got most of it.
Okay.
I understand that way.
I feel like I'm confusing you. I'm sorry.
No, you're,
Okay.
I'm more clear than I was before.
Yeah.
Okay. Anybody else? All right. If not, that's all I got. You're welcome, Carol. Thank you guys for coming.
Are you gonna have a study session before the test?
Mhm.
Is it the review?
Yeah.
What would be on it?
Yeah. Yeah, well, I'll do like a test review study session. Probably, yeah, I guess the Wednesday before the test.
Are the tests hard?
Hmm?
Are the tests hard?
No, I don't think so. Especially now they're open note, open book. I don't think they're hard. The biggest problem I had was time.
Yeah, does it take 2 hours?
Yeah. I mean, for pretty much all the tests, I was going like right up to the deadline, and I'm a pretty fast test taker generally. So
Dude, stop.
I'll just tell you, my tip is if you don't know something, don't get caught up trying to flip through the book to find it. Just if you have time, come back later, but don't get too caught up in trying to flip through all of your notes.
Is it like that many questions, or is there really just like 2?
No, normally it's kind of like I don't know. I can't remember how many he had on the first one. It was probably like 10 or so, and then, but each one will have different parts, and some of them will like take longer than I really don't think that tests are bad. I personally thought like the homework is always harder than the tests.
Yeah, I looked at the homework today. I was so
Yeah.
confused.
Yeah, some of it is confusing.
I was